A statistics professor plans to travel to a conference by plane. When he passes the security check, they discover a bomb in his carry-on luggage. Of course, he is hauled off immediately for interrogation. I don't understand it, the interrogating officer exclaims. You're an accomplished professional, a caring family man, a pillar of your parish, and now you want to destroy that all by blowing up a plane? Sorry, the professor interrupted him. I had never intended to blow up the airplane. So, for what reason did you bring a bomb on board? Let me explain. Statistics shows that the probability of a bomb being on an airplane is 1 out of 1,000. That's quite high if you think about it. So high that I wouldn't have any peace of mind on the flight. And what does that have to do with you bringing a bomb aboard the plane? You see, since the probability of one bomb being on my plane is 1 out of 1,000, the chance that there are two is 1 out of 1,000,000. If I already bring one, the chance of another bomb being on around is actually 1 out of 1,000,000, and I am so much safer. All right, and now we start our probability unit. And a random phenomena is a situation in which we know what outcomes could happen, but we don't know which particular outcome will happen. So for any random phenomena, we're going to be dealing with trials, and we're going to generate the outcome. The outcome is what happens during the trials. Then I couldn't do black, so I did white and silver, or gray, and I set those both to 25%. So based on these areas, you would predict that, let's say I did a total of 4 spins, I would have 2 purples, 1 white, and 1 gray, right? So that's what I would predict. And on one spin, I would get a 50-50 shot of getting purple. So let's see what happens when I went ahead and played with this spinner. So here we go. Purple. That's fine. Let's do it again. Purple. Wait a second. I'm at 100%. The next one can't be purple, but it is. Well, not the next one. We won't have another purple. Got another purple. The spinner must be broken, don't you think? Let's try again. Okay, we got another purple. We got 100%. And another purple. 6 purples in a row. Wow. Finally, we got a white. Okay, it'll settle down now. Wait, we got another purple. And then a purple. I thought we were going to get a gray on that one. And a gray finally. So the thing is, this is not behaving very well. Why is that? We've only been doing 1 spin at a time. Now when we start adding more spins, you can see that the percentages are getting much closer to the predicted. Let me add 1,000 spins. And in the long term, yes, I got purple 50% of the time, and the white and gray each about 25% of the time. So it behaved. So the point is, when you're looking at individual events, probability is great, but it's not going to tell you for sure what's going to happen. It will give you a very good rough idea of what will happen in the long term if things are behaving as they should. So, can you predict what the next spin will be on the spinner? No, you cannot predict each spin. The law of large numbers says that the long-run relative frequency of the repeated independent events gets closer and closer to the actual or true relative frequency as the number of trials increase. So, how do we interpret probability? Here I've given you a sort of framework here. If you take a very large sample of whatever's in your problem, about whatever probability of them will be whatever it's supposed to be. So how do I use that to interpret this? What does it mean that the probability of purple is 50%? I will say if you take a very large sample of spins, notice I put of spins in there, about 50% of them will land on purple. The common misunderstanding of the law of large numbers is that random phenomena are somehow supposed to compensate for whatever happened in the past, but this simply is not true. So if you flip the fair coin and you got heads on each of the first 10 flips, what do you think is the chance that tails will come up on the next flip? Well, some people might say, oh, it's got to be tails the next time. Well, on the spinner, I thought for sure it wasn't going to be purple, but it kept showing up purple. The probability is going to still be 50%. The coin's not going to remember what you flipped before. Neither did the spinner. Now, let's say you have a job to do. The management at Let's Make a Deal, I don't know if you've heard of the game show, wants your estimate of how often someone will lose this new game called Race to the Finish before getting at least one prize. So here's how you do it. You keep drawing cards until you either win or lose. If you draw 5 hearts before you get 4 spades, 3 diamonds, or 3 clubs, you win a car. If you get 4 spades before you get any of the other combos, you win a trip. If you get 3 diamonds, you win a computer. And if you get 3 clubs, bum, 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 you lose. All right. So what are the challenges to this question? They're trying to have you do some predictions for them. First of all, we don't have any formulas yet. And secondly, the game depends on randomness, which means you won't know what outcome will happen, even if you know all the possible outcomes. All right. And you don't know which card is going to be drawn, but you do know which cards could be drawn. And you can only provide an estimate of the probability, and that's nice. So they're saying, well, we want to know roughly how we're going to do, because honestly, we are never certain of anything in statistics. It's beautiful. All right. So we're going to do something called a simulation, which is recreating a random process. Our model should be as close to the real life situation as possible. It should have a component, so they're little parts of our little trial, and it models a random event. In our case, our component could be drawing a card, all right? And then a list of possible outcomes. So the possible outcomes for each component is either a heart, a spade, a diamond, or a club. And then we have to determine how often each outcome should occur. So there are 13 of each of these decks in the cards. So how am I going to say what represents a heart, a spade, a diamond, and a club? Well, I'm going to use what's called a random number table. And I'm going to assign, which I'm showing here. So I'm going to, in real life, what I would do actually before I use a random number table is I could shuffle a deck of cards and just play, right? So let's say my response variable is going to be win or loss. And I actually play out, I draw a 9 and then a 7 and then a 4 and then a 7. And you can see I hit 3 diamonds. So in this case, that would be a win. So I would keep a tally here. I have a win in the win column. Then I'm going to draw another set of cards. I've got a club, a spade, a club, a spade, a heart, a club. That would be a loss. So one easy way to do a simulation is just to go ahead and play the game. That's kind of like what we do in our little project with the carnival game. Another way you can do a simulation is use something like a random number table. So random number tables, or even a random number generator, that also works. They're just basically lists of numbers that have been generated randomly. They actually have people who officially do this. And we can use these lists of random numbers so it takes our brain out of the equation. So we're going to say, since we're using numbers, and I'm going to use 2 digits to represent a card. Why 2 digits? Well, if there are 13 clubs, 13 diamonds, 13 spades, and 13 hearts, then I need 52 different possible outcomes because I'm trying to represent an actual deck of cards. Then I'm also going to make sure that anything that, the reason I did 0, 0 to 12, I said, well, let me start at the beginning. The lowest possible 2-digit number I can get is 0, 0. So I need 2 digits to get to 51. And then that gets me to 51, so I can represent all the cards. Okay? So I'm going to take a look at the first 2 digits. 16, that's over here in diamonds. So those first 2 digits right there is a diamond. 40. That would be here in hearts. 88, well, since that's outside of my range, I'm going to ignore, and you do need to specify what you're going to ignore. That, I'm just going to ignore the 88. 18, that's over here in the diamond section. 99 is too high. 4 is a club. So let's see, we've got 2 diamonds, 1 heart, and 1 club. We're still playing. 15 is a diamond. Ah, looks like I win. In this case, I win a computer. So I can say, ah, On my first trial, it looks like the person wins the computer. Let's go on to the next trial. 35, that's a spade. 33, that's a spade. Ooh. 81, that is too high. We've got to ignore it. 79 is too high. 40 is a heart. 12 is a club. Well, we've gotten pretty far. I think we're going to do pretty well here. 14 is a diamond. 38 is a spade. I do believe that's, no, I need 4 spades. Next card is too high, and 3 is a club. Then 59 is too high. 23 is a diamond. 50 is a heart. And let's see, we got 3 spades, 2 clubs, 2 hearts, 2 diamonds. We're very close. 36 is a spade, and I think that gets me my 4 spades. Ooh, I want a trip. Okay, let's start again. So this is trial 1 right here. Here's trial 2. 69 is too high. 33, so we're pretending the whole deck's available again. 33 would be a spade. 12 is a club. 38 is a spade. 59 is ignore. 64 ignore. 99 ignore. 17 is a diamond. So we got 2 spades, a club, and a diamond. 54 too high, ignore. 72 too high. 77 too high. 20 is a diamond. So for our 2 spades, 2 diamonds, 1 club. 23 is also a diamond. I think that is a win. 3 diamonds, win a computer. All right, so far we had them win a computer, they won a trip, and then they won a computer again. All right, next one. 38 is a spade. 18 is a diamond. 62, ignore. 98, ignore. 19 is a diamond. 53 is too high. 5 is a club. 52, oh, that's too high. 9 is a club. 19, now why the heck did I ignore 19? Well, I already had a 19. I'll go ahead and finish playing. I already have a 19 right here. And if I had already drawn that card, I'm not allowed to draw it again in this particular game. All right, so that 19 is a repeat. So we'll keep going. We got the 62 is too high. A 4 is a club. Oh, I think that gives me 4 clubs. Ah, we lose. And then if I keep playing one more game, we go 73 is too high, 91 is too high, 30 is a spade, 92 is too high, 97 and 66 are too high, 22 is a diamond, 48 is a heart, 22, oh, I have to ignore that one because it's a repeat. Ignore the 94 because it's too high. 73 is too high. 00 is a club. 64 is too high. 96 is too high. 3 is a club. So we got 2 clubs, 1 spade, 1 diamond, 1 heart. 93 is too high, and then we get a club, and that is a loss as well. So I could tell my employers, well, looks like they won a computer twice, they won a trip once, and they only lost twice. So most of the time on this game, it looks like they will be winning. So the race to the finish, the statistic, I could actually report the amount of wins and losses based on the simulation. Now remember, this will be an estimate. This is not 100% theoretical probability, which is where we say, oh, we know how it behaves, so it should absolutely be this. Although, again, it's random, so we never know for sure. Well, no, the theoretical, we just can't predict what will happen actually. All right, so let's go ahead and look at some examples. We have a basketball player, and she has an 80% free throw success rate. How do we simulate whether she makes a foul shot? How many shots might she be able to make in a row without missing? So how would I simulate this? I know 80% of the time she's good. So how many digits do I have in that number? 2. So I probably am going to want to use 2 digits if I'm using random numbers. So the component is the thing that we're going to simulate, the little piece of it is taking 1 shot. Actually, I could do 1 digit. Now that I think about it, I could get a random digit from 0 to 9. because 80% is 8 out of 10. So you see how I can just do one digit? So if we'll say 0 to 7 is a good shot. Why 0 to 7? 0, 1, 2, 3, 4, 5, 6, 7. That's 8 fingers. So that's 8 out of 10 fingers. That's 80%. And then we'll say the other two higher digits, 8 and 9, are a miss. The trial is taking the shots until she misses. Since a miss is 8 or 9, then stop on the first 8 or 9 you see. The response variable is the number of shots made before the miss, and the statistic is the mean number of shots made. All right, now let's say she didn't have to do an 80% free throw and we changed her success rate to 72%. That one we really do want two random digits. So we could go 0, 0 to 71 is a good shot, and then 72 and higher is a miss. So we take the shots till we miss, until she misses, and since a miss is 72 or 99, stop on the first two digits in our pair that is 72 or higher. So how would a trial and our response variable change if we want to know how many shots she might make out of 5 attempts? In that case, the trial is just look at 5 pairs of digits, right? So, and then we'd say the number of shots she makes out of the 5 attempts and the number of pairs we get from 0, 0 to 71. So again, what we know is she's just doing 5 shots. So we'll look at one pair. Did she make it? The second pair. Did she make it? The third pair. Did she make it? The fourth pair. Did she make it? And the fifth pair. Did she make it? And what if she was in a 1-on-1 situation? That means she gets to take a second shot if she makes the first one. Well, look at the first pair of digits. If the first pair is made, then look at the second pair of digits and stop at 2 pairs. And you could say the response variable is the number of points she makes in a 1-on-1 situation. So the statistic could be the mean number of points. Usually you'll be asked, what statistic you're trying to gather. So let's go ahead and actually look at a 1-on-1 situation because that's a little different. We have a basketball player has a 65% free throw success rate on her first shot in a 1-on-1 situation. She has an 80% free throw success rate on the second shot. So if she's already made one shot, usually like, okay, all right, we're pretty confident, we know what we're doing. We did the shot correctly, so we probably have everything calibrated. So our percentage of getting it again is even higher. So our component is taking a shot. And we're going to use digits from 0, 0 to 99. If this had been 60, I could have used one digit. But because it's 65, I really need two. So we're going to look at the first pair of digits. All right, that's her first shot. If the first pair is 0, 0 to 64, what does that mean? She made it because that's 65% of the digits. I know it says 64, but when we add that little puppy in, it makes 65. You could ask, why do we always start at 0, 0? Wouldn't it be easier to just go 0, 1 to 65? You could. And technically you can. That's allowed. The problem is that people don't say what to do with the 0, 0 and they forget. You have to say that both the in this case, 65 and higher is a miss. But if you did 0, 1 to 65, you'd have to say 66 to 99 is a miss, and you'd also have to say that 0, 0 is a miss. So it's usually cleaner to start at 0, 0. All right, so if her first pair is in there and she makes the shot, then we get to go ahead and look at her second shot. Remember, in a 1-on-1 situation, if you make the first shot, you get to try a second one. If you miss the first shot, you're done. So since she has a higher percentage there, then the values for the second pair is actually going to change. It goes from 0, 0 to 79, and anything higher is a miss. Technically, I should be listing what the misses are here. So the response variable is the number of points she makes in a 1-on-1 situation. And the statistic, you could say, is the mean number of points, which makes sense. How many 1-on-1 situations? You look at the average that she got in those. So we're going to go ahead and actually do another simulation. And I've got a list of random numbers here, which should be enough for our 10 trials. And one other thing, a frequent question I get is, why is there a gap between these numbers when we see them? It's just for readability issues. It's not how you're supposed to break up the numbers. So let's go ahead. First shot, 42. Did she make it or miss it? Did she get a point or not? She gets a point for that one because she made it. 27 is also a make because that's from 0, 0 to 7, 9. All right, so she made the point. So there, she got 2 points on that trial. Next trial, she has an 81 on the first shot. That's a miss, so no points there. Then the next trial, she has a 21, that's a point, and a 60, because 21 is less than 60, is in the 0, 0 to 64. 60 is in the 0, 0 to 79. That's also a point. So she gets 2 points there. So she had 2 points, no points, 2 points. Next one. Here she gets a point because it's 0, 0 to 64. This one is 0, 0 to 79. That's also a point. Here we have 0, 0 to 64. That's a point. And 0, 0 to 79, 42 is definitely in that. That's a point. So far we've made one attempt trial with 2 points, one trial with 0 points, another trial with 2, another trial with 2, another trial with 2. She's doing pretty well. But this next one, 78, for her first attempt. If it had been her second, it would have been okay, but it's her first attempt, and she has to be in 0, 0 to 64. So that's going to be a miss. Then we have, let's see, how many shots? 1, 2, 3, 4, 5, 6, 4 more shots. That's definitely a point and a point, so she makes that. There's another point and a point, so that should be about 8 shots. That's a point and definitely a point. Then we have a miss, and that's basically your 10 shots right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So, interestingly enough, every time she made the first shot in our trial, she got the second shot, which kind of makes sense because her percentages on the second shot are much higher. But she did have a few misses in there, so you can see that. So her statistic, if I wanted to average the mean of the points, it would be the 14 points divided by the 10 trials, or 1.4 points per attempt.